Alright, hi everyone. Let's solve our first example using Gauss law. We are going to tackle question 37. Let's read the question first. Question 37. A sphere of radius uppercase R has a uniform volume charge density of rho 0. Find an expression for the electric field at any point inside the sphere, and I will add an extra part to this question. Find the electric field outside the sphere also. So the first thing is, in question 37, you're shown a diagram of a sphere. It is a charged sphere. So here, I've drawn a diagram, the charged sphere in black ink, all right? Now, we want to find the electric field inside that charged object. Now, by the way, it's not a conducting sphere, it is a non-conducting sphere. So in this case, we are told that there's a uniform charge distribution. That's a key word to let us know that we can use spherical symmetry. In other words, if we draw a sphere inside our sphere, the electric field on the surface at all points will be constant. So what we do here to calculate the electric field inside that charged sphere is we draw what we call a Gaussian sphere. Now, an important characteristic of the Gaussian sphere is the center has to be aligned with the center of the spherical object. Both centers need to be exactly at the same place. The reason for that is we draw a Gaussian sphere, and because both centers are aligned, and because the charge distribution is uniform, the electric field on the surface of the Gaussian sphere over here will be constant everywhere. Because it is constant everywhere, we can use Gauss law. So Gauss law, and this section of Gauss law, state that the electric field multiplied by the area is equal to the charge divided by epsilon 0. There's two important parts here. The area here is the area of our Gaussian sphere, not the area of the object. It is the area of the Gaussian sphere always. Always. This is a very common mistake, all right? We are considering this imaginary construct here, the Gaussian sphere, and it's the surface over here that we are considering. Next, the second part that creates a lot of confusion is the charge. Well, the Gauss law is related to closed surface, the charge inside a closed surface. Well, our closed surface in this case is the Gaussian sphere. So this is the charge inside our Gaussian sphere. Inside. If you pick a charge over here, it's not included in the Gaussian sphere. It has to be inside. All right. So how do we calculate the area? Well, the area is really straightforward. It's a sphere. Area is equal to 4 pi r squared. Simple as that. Now the r is the radius of the Gaussian sphere over here. So do not confuse with the radius of the object in this case. We will need the radius of the object when we want to calculate the electric field outside the sphere. Second part is we need to find the charge. Again, it is the charge inside our Gaussian sphere. And one thing that is different when we are dealing with object is we are talking about charge distribution. Rho 0 is the amount of charge per meter cube. So if you want to know the amount of charge inside the Gaussian sphere over here, you have to multiply the amount of charge per meter cube. And remember, in this section and in this course, this number is a constant. It does not change wherever you are inside the sphere. It is constant. Therefore, if you want to know the charge, multiply amount of charge per volume multiplied by the volume in meters squared. Well, the volume, this is a sphere. The volume of a sphere is 4 divided by 3 pi r to the cube. All right? Again, it's the radius of the Gaussian sphere, not the radius of the bigger sphere. At least while we are considering the electric field inside the sphere. All right? So at this point, we got Q and A, and these are always the two challenging values. Generally, the electric field, well, you could be given the electric field and asked to reverse engineer and let's say find the volume charge density. That's a possible question. But most of the time, you need to find the area, the charge, and then you find the electric field. And you need to find the charge using the charge density. All right, so inside the sphere, we take the area, we flip it on that side. We got electric field is equal to the charge inside the Gaussian sphere divided by the surface area of the Gaussian sphere multiplied by epsilon 0. We replace Q and A by these two terms. We get that format over here. Notice there's a lot of terms that cancel out. We end up with the volume charge density multiplied by the radius or the distance from the center divided by 3 multiplied by epsilon 0. So this is our expression. The electric field inside the charge object is given by this relationship. Now obviously we consider in this case on the diagram a smaller sphere, but notice we can just change the R to consider any point inside the sphere. Now in the second part of the question there's a catch. Once we exit the sphere, once we create a Gaussian sphere that is bigger than our object, there's an important distinction. The charge over here stops growing. If you notice this term over here, the electric field gets bigger and bigger as you go away from the center. And it's a bit counterintuitive at the beginning. If you get farther away from a charge, the electric field goes lower. The reason why this is not the case here is because as you move farther away from the center, the number of charge inside your object grow bigger and bigger. Therefore, the electric field is increasing. But once you get outside the object, well, the charge is then fixed. It does not grow bigger and bigger. So here, we would still use the same formula to find our charge inside the object, but since it's not dependent on the radius of our Gaussian sphere, in the second part when we are considering the field outside, we are creating a Gaussian sphere that is bigger than the object, so our R becomes bigger than the R of the object. If we want to calculate the charge inside that sphere, we now need to use the R of the object. All right? So that's what we do here. So E, again, same formula. The Q over here is equal to 4 divided by 3 pi R to the cube, and again multiplied by the volume charge density. The bottom part did not change. We are still considering the area of our Gaussian sphere. It's just the charge that changed at that point. Now, we end up with this definition over here. Now, if we don't replace the Q and keep Q as it is, we end up with only the bottom part. So Q divided by 4 pi R squared epsilon multiplied by epsilon 0. One thing we did not talk about in the first and second chapter is the Coulomb constant is related to epsilon 0. Actually, the Coulomb constant is equal to 1 divided by 4 pi multiplied by epsilon 0. In other words, we get exactly the same definition for the Coulomb force and the electric field using Gauss' law than we did in chapter 1 and 2. The two tricks converge, they show the same answer, and that's important in physics. All the methods need to lead to the same answer, otherwise they are invalid. All right, so that's it for question 37. We're going to solve many more problems in this chapter just to make sure all these concepts sink in. All right, so see you in the next video.